Awak yang tu lah. Jangan lupa subscribe channel kita, tanda sokongan. Terima kasih. Assalamualaikum and hi everyone. Welcome back to my channel. Okay, so kali ni anda bersama saya, Madam Fiki. Okay, rasa macam dah lama saya tak buat video. Okay, saya tahu awak pun semua busy dengan jadual yang semakin padat. Okay, jadi kita akan sambung chapter 5. Okay, part 1. Alright, on chapter Electromagnetic Induction. Okay, so in this chapter we are going to discuss some examples that related to chapter 5. Okay, but before we start to discuss the examples, we are going to recall some short notes or some points, okay, to highlight the important points before we answer the question. Okay, so I will go through some short points or short notes in order to recall about the electromagnetic inductions, about the Faraday's Law, and also the Lenzs Law. I'm pretty sure that you already know what is the induced EMF, what is the induced current, what is Faraday's Law, and what is the Lenzs Law, and so on. Okay, so look at here, we have the electromagnetic induction. Okay, so what is the electromagnetic induction? Okay, so it's basically the production of induced EMF, okay, or induced voltage, alright, or induced current whenever there is a magnetic flux change. Okay, bila ada perubahan magnetic flux dalam loop, coil or circuit. Okay, bila ada perubahan dalam magnetic flux, kemudian akan ada induced EMF. So this is related to the Faraday's Law, okay, which is the equation is equal to EMF is equal to, ingat lagi tak? EMF is equal to negative N d phi over dt. Alright, so electromagnetic induction basically related to the changing in the magnetic flux. Ada perubahan magnetic flux, okay, terhasillah electromagnetic induction. Okay, and macam mana berlakunya electromagnetic induction? When there is a relative motion of loop. Okay, bila ada pergerakan loop. Okay, pergerakan loop dengan apa? When a relative motion between loop and magnetic field lines. Okay, and the loop and the magnetic field lines are cut. Okay, maknanya bila loop itu bergerak, dia memotong magnetic field lines itu. Okay, so terdapat perubahan magnetic flux. Okay, itu secara basic lah yang you kena faham. Okay, so selain pada itu, you must know that the number of magnetic field lines passing through a coil are increased or decreased. Okay, so bila ada pergerakan loop tersebut ataupun coil bergerak, so there is a different number of magnetic field lines that passing through a coil or through a loop. Okay, so there is a change of a number of magnetic field lines that passing through a loop. So bila ada perubahan magnetic field lines yang lalu coil tersebut ataupun passing through a coil, means that there is a change in the magnetic flux. Okay, alright. Okay, so how to increase the induced EMF? Okay, look at here, we have 4 points here. So the first one, we use a stronger magnet that can increase magnetic flux. Second, push the magnet faster into the coil to increase speed. The third one, the area of the coil is greater. Okay, and the last one is the number of turns can be increased. Okay, look at here. We just want to recall about Faraday's Law and Lenzs Law. Okay, so the Faraday's Law states that the magnitude of the induced EMF, so this is the symbol for the induced EMF, is proportional, berkadar terus, okay, to the rate of change. Bila ada perkataan rate, mesti berkait rapat dengan perubahan masa. The rate of change of the magnetic flux. this is the change of the magnetic flux over the change of time. Okay, d phi over dt. Okay, d phi over dt here is rate of change of the magnetic flux. Okay, kalau ini sahaja, d phi sahaja, ini adalah change of the magnetic flux. Okay, over bila dia bahagi dengan masa, kita sebut dia sebagai rate of change of the magnetic flux. Alright, okay, bila ada perubahan magnetic flux, okay, bahagi masa, perubahan masa, okay, akan hasilkan induced EMF. Okay, so here we have the change of the magnetic flux. Okay, the magnetic flux final minus magnetic flux initial. Alright. Okay, so the negative sign indicates that the direction of the induced EMF always oppose the change of the magnetic flux producing it. Okay, and this is referred to Lenz's law. Kita akan tengok sekejap lagi macam mana kita nak apply Lenz's law in order to determine the direction of the induced current. Okay, so here we have Lenz's law. The definition of the Lenz's law here, okay, the Lenz's law state that an induced electric current always flows, okay, in such a direction that it opposes the change producing it. So in order to determine the direction of the induced current, okay, we need to know that the induced electric current always flows in such direction that it try to oppose the change producing it. Okay, apa maksud dia? Macam mana kita nak apply sekejap lagi? Jom kita tengok. Okay, so this is the Lenz's law. Okay, so we have several figures here. Alright, so when an EMF is generated by a change in magnetic flux according to Faraday's law, okay, bila ada perubahan magnetic flux, so akan terhasillah EMF according to Faraday's law. Okay, so the polarity of the induced EMF is such that it produces a current whose magnetic field oppose the change which produce it. Apa maksud dia? Polarity of the induced EMF ni akan terbentuk ataupun akan terhasil ataupun dia menghasilkan current di mana the direction of current, okay, we need to determine the direction of current where the magnetic field oppose the change which produce it. Okay, you must know that the induced magnetic field inside any loop of wire always acts to keep the magnetic flux in the loop constant. Alright, look at here. So we have figure A here. So this is the initial condition of the loop. Alright, where I is equal to 0. No current flow, okay, in the loop. Alright, so no motion. Alright, so initially the position of the bar magnet is at this position, right? Okay, so this is the north pole and this is the south pole. Alright, and the direction of the magnetic field from the bar magnet is in this direction. Remember, we must draw the direction of the field lines from north pole to south pole. Sebab tu direction dia ke bawah macam ni lah. Okay, north pole to south pole, north pole to south pole. Alright, so this is the initial condition. Alright, okay, for the figure B, okay, so what happened when this bar magnet move closer to this loop? Okay, so means that the magnetic field around this loop or the magnetic field in the loop will increase. Okay, bar magnet tadi dia sendiri ada magnetic field, right? But the loop of wire always acts to keep the magnetic flux in the loop constant. Means that this loop will produce an induced magnetic field, okay, where this induced magnetic field will act in opposite direction, okay, which is upward, okay, which is opposite direction, which is upward, in order to oppose the change of the magnetic field around the loop. Okay, maksudnya apa tadi? Bila bar magnet datang dekat loop ni, apa yang berlaku? Loop ni akan jadi apa? So, the magnetic field will increasing in the loop. Okay, so suddenly what happened? Okay, the loop we try to oppose the change of B. Okay, kalau bar magnet datang dekat, B akan increase, right? Tapi loop akan try to oppose. Okay, so in order to oppose the change of the magnetic field, okay, so dia akan hasilkan satu induced magnetic field inside the loop. Okay, sebab apa? Sebab dia nak keep the magnetic flux in the loop constant. Okay, so if the B field is increasing, the induced field acts in opposition to it. Okay, apa contohnya macam ini? So bila dia datang dekat, okay, so magnetic field ke sini, arah sini downward, okay, sini north, south. So bahagian atas loop akan jadi north dan ini akan jadi south. Okay, so let's write. So let's try to write here. We have north here. Okay, and this is south. Okay, so north, dia akan try to oppose lah. Dia akan try to oppose the motion of the bar magnet. Bar magnet nak datang dekat, okay, they try to oppose, so automatically the top of the coil or the top of the loop will become north pole and the bottom of the loop will become south pole. Alright, so in order to determine the direction of the induced current, okay, so by using your right hand, okay, let's change to laser. Okay, in order to use your right hand here, okay, so right hand grip rule, okay, make sure you keluarkan tangan kanan awak. Your thumb must be pointing to the north. Alright, so upward, and look at your other fingers, the direction of your other fingers, okay, which is anti-clockwise. Okay, tengoklah arrow tu anti-clockwise. Okay, look at here. Okay, this is your fingers, so it's anti-clockwise in this direction. Boleh? Okay, but what happened if the bar magnet try to move away from the loop? Bila bar magnet nak pergi jauh daripada loop ini, okay, so the magnetic field will decrease in the loop. Betul? The magnetic field around here will decrease, but the loop will try to keep the magnetic flux in the loop constant. So the induced magnetic field will act in the same direction. So means that here we are going to have, so here we have north pole, right? So when the bar magnet is moved away from the loop, so here this point, the top of the loop will become south pole, and here, okay, the bottom of the loop will become north pole. Okay, alright, so you can see here, okay, this is the north pole and this is the south pole of the bar magnet. And when the bar magnet move away from the coil, and the loop will try to attract some magnetic field, okay, so north and south, so automatically magnetic field B ni akan pergi ke sini lah, in the same direction. You can see here, okay, B from the magnet and the induced B secondary is in the same direction. So ada yang kata, alright, so bila bar magnet pergi jauh, okay, so the coil will try to attract the magnetic field from the bar magnet. So automatically sini akan jadi south, sini akan jadi north. Kalau bar magnet tu datang dekat, okay, the coil will try to oppose the magnetic field from the bar magnet. Alright, so north, so sini akan jadi north, sini akan jadi south tadi. Okay, okay, now by using your right hand grip rule, okay, your thumb must be pointing to north pole, which is downward. Alright, so letak tangan kanan awak downward, and then look at here, your other fingers must be curled in this direction, which is clockwise direction. Okay, alright, good. Okay, here we have other diagram in order to explain about the Lenzs law. Okay, this is the some examples. So look at here, if B field is increasing, okay, B field, the magnetic field is increasing, means that Okay, bila B increasing tu maksudnya bar magnet tu datang dekat pada solenoid, datang dekat pada coil tersebut. Okay, so the induced field. Okay, so the induced field is referred to the magnetic field that induced in the coil ataupun in the solenoid. Alright, and it will act in the opposite direction. Okay, look at here. When the bar magnet is come closer to the coil or to the solenoid, so we have north pole here. Okay, bila dia datang dekat, automatically the magnetic field around this area will increase. Betul? But this solenoid, okay, akan cuba untuk apa? This solenoid will try to keep its magnetic flux inside the coil constant. Dia akan try to maintain its initial condition. Okay, they try to keep it constant. Therefore, there is an induced magnetic field in opposite direction. So, in order to oppose the direction of the magnetic field from the bar magnet, okay, direction of the magnetic field, tengok sini, to the left, sebab north kat sini kan. So, B to the left lah. Okay, magnetic field mesti keluar daripada north pole. Therefore, the direction of the induced magnetic field mesti opposite direction. Sebab dia tak nak increase B. Dia nak lawan. Dia tak nak increase B. Okay, dia nak kurangkan. Okay, dia nak lawan. So, they'll try to oppose the change of the magnetic field. Okay, inside the solenoid. Therefore, this side, okay, let's say, this side will become, okay, saya tulis. So, this side would become north and this side would become south pole. Okay, so caranya sekarang, okay, saya letak video di sebelah kanan, awak boleh tengok okay, so awak ambil tangan kanan awak, okay, alright, so now by using your right hand grip rule, okay, so this is your right hand, so your thumb will pointing to the north pole. Alright, so since the north pole is on the right side of the solenoid, so okay, put your right hand, okay, like here. So we have, okay, awak genggamkan pen awak, so belakang dia akan jadi macam ni, ataupun you ada botol, okay, ataupun dia macam ni lah, upward. So the direction of the induced current, okay, at the back of the solenoid is upward and depan adalah downward. So you can see here, okay, so you can see here the direction of current is in this direction, downward. So wire yang depan ini semua downward lah. Okay, so here we have positive and negative. Alright, because current will flow from positive to negative, right? So kita letak sini lah, positive, the induced EMF, so positive and negative. Boleh? Okay, so for this one, okay, let's say kita soalan bagi this is the south pole and the condition is the bar magnet is moved away from the solenoid. So when the bar magnet is moved away from the solenoid, what happened? Okay, what happened to the magnetic field in this area? Okay, bar magnet pergi jauh ni. Alright, so the magnetic field in this area will decrease. Tengok sini. If it is decreasing, okay, bila magnetic field decreasing, induced magnetic field will act in the same direction as the applied field. Okay, sekarang tengok ya, the direction of the applied field. So this is the direction of the applied magnetic field. So direction field dia macam ni lah. Kenapa arrow dia macam ni? Ada yang tanya lagi, kenapa arrow dia macam ni? So south, north. So dia akan keluar macam ini, north and pergi kepada south, north pergi kepada south. Okay, so B dia ke sini lah. Okay, so when the bar magnet is moved away to the solenoid, so what happened? The magnetic field in this around decrease, but the solenoid will try to keep the magnetic flux in this solenoid constant. So dia tak nak berubah pun dia punya the amount of the magnetic field strength. Okay, therefore this solenoid will try to keep the amount of magnetic field around it constant. Okay, so we need to write here, Okay, so if this is south, this side will become north pole in order to attract some magnetic field from the bar magnet. Bar magnet nak pergi jauh ni. So we want to attract some magnetic field in order to maintain the magnetic field or the magnetic flux. Okay, inside the coil ataupun inside the solenoid. So this one should become south. Boleh? Alright. So now by using your right hand grip rule, okay, watch the video. Okay, by using your right hand grip rule. So now please point your thumb to the north pole, which is to the right. So the back of the solenoid, the direction of current is upward. Okay, tapi yang depan, okay, depan solenoid will be downward. Okay, so dia akan jadi macam ni lah, downward. So kita akan dapat downward. Dan seterusnya. Yang dua ni awak boleh cuba sendiri. Okay? Okay, good. So this is the revision again. So this is the equation of the Faraday's law. There is an induced EMF when there is the change of magnetic flux over time, or there is an induced EMF when there is a rate change of magnetic flux. Okay, so the equation of the magnetic flux is BA cos theta. I don't think you have problem to use the equation. Okay, and okay, so this is the explanation about the Faraday's experiment, Faraday's law, and also the Lenz's law. Okay, so Faraday's experiment state that a steady magnetic flux or field produce no current. If the magnetic flux steady, tidak berubah, maksudnya tak ada current. Okay, tapi when there is a changing in magnetic flux, okay, or there is a changing in the magnetic field, and these changes can produce an electric current, and we call it as induced current. Okay, secara ringkasnya. And Faraday's law, okay, state that the magnitude of the induced EMF, okay, this one is directly proportional with the rate change of the magnetic flux. Okay, d phi over dt. And Lenz's law, okay, so Lenz's law state that the induced current, the induced electric current always flows. So this one is basically the direction of the induced current in such a direction that it opposes the change producing it. The change producing it means that it tries to oppose the change in increase in magnetic field or decrease in magnetic field. Okay, so yeah. Okay, alright, how can we induce EMF? Okay, so the first one, okay, let's say we have the straight conductor and we try to move the conductor in a magnetic field. You ada conductor, you try gerakkan conductor pada magnetic field, then you can induce the EMF, or you can get the induced current. Ataupun you rotate the coil when the coil is rotating, like this one. Okay, when the coil is rotating. So this one is rotating coil in a magnetic field. So we have north and south pole here. We have the magnet. Okay, bila ada north and south pole, means that we have the magnetic field lines from north to south pole. So bila ada coil that rotate in between these field lines, so akan hasilkan induced EMF. Okay, or by changing area in magnetic field. Okay, or the last one by changing magnetic field strength. Okay, now look at here. We have some equations, and I'm sure you have learned about how to use these all equations, right? Okay, so the first one, the induced EMF in a plane coil by changing area. Okay, so this is the equation from the Faraday's law, where flux is equal to BA cos theta. When you substitute in this equation, we can relate that induced EMF is equal to, so let's bring B and N and also cos theta at the front of the equation. Okay, let's say N, the number of turns, B is the magnetic field, and cos theta, the angle between A and B, is constant. Kesemua ini constant, but we have dA over dt. Okay, the rate change of area. Maknanya area dia berubah. So by stretching the coil, we reduce the area of the coil. Look at this diagram. So when we try to stretch the coil, you can see here, for the second diagram, okay, the amount of magnetic, you can see the cross symbol means that this is the amount of magnetic field that pass through this area. So for the second diagram here, obviously we can see that the amount of magnetic field that pass through the second diagram is reducing. Alright? Kalau compare dengan gambar pertama ni banyak kan? Dot pula. Cross compared to this one. Therefore, the current is induced in the coil. Bila ada perubahan area, okay, there is a change in the magnetic flux. Okay, yang macam ni pula, apa dia faktor yang mempengaruhi induced EMF? So, induced EMF in a plain coil by changing magnetic field. Okay, B. Okay, so let's say initially the magnetic field B is 50 Tesla. Okay, and then you change the magnetic field strength from 50 Tesla to 100 Tesla. You try to increase the amount of magnetic field. Bila terdapat perubahan magnetic field strength, so dB over dt, okay, this equation, let's try to rearrange this equation. Bawa A pergi depan sebab A constant. In this case sekarang A tidak berubah, A constant, cos theta, the angle pun constant, the angle between B and A also constant. Okay, sekarang apa yang berubah? B yang berubah. B is changing, dB over dt. So this is the rate change of magnetic field. So as the magnetic field strength B is increasing or decreasing with the time, okay, the magnetic flux through the area also changes. Therefore, induced EMF in the coil will produce. Boleh? Okay, so this is the equation. Okay, and next, if we try to rotate the coil, okay, so the equation of rotating coil, so this is the derivation, so come from the equation of the Faraday's law, okay, BA cos theta. Remember, theta is the angular displacement since this related to the rotational motion. So theta angular displacement is equal to angular velocity times t ataupun angular speed times t time. Okay, so kita gantikanlah cos omega t. So differentiate cos omega t give you omega sin omega t. Okay, tahu tak macam mana nak differentiate ni? Remember, the first semester you have learned how to differentiate, right? Okay, differentiate cos omega t give you sin omega t, and then differentiate again omega t, alright, respect to t, and then it will give you omega. Alright, so you akan dapat induced EMF is equal to NBA omega sin omega t. Okay, so next, induced EMF in a straight conductor moving through a magnetic field. Okay, so we will produce an induced EMF, okay, as we have a conductor, okay, that is moved through a magnetic field. So the cross symbol here, okay, indicates the amount of magnetic field in this area. So current will induce, and look at here, we have the bulb. Okay, what happened to the bulb? The bulb is lightened up. Alright, so maknanya ada current yang lalu bila conductor ini bergerak ke kiri. Okay, once the conductor is moved to the left, suddenly this bulb is lightened up. Therefore, we can conclude there is a flow of current in this circuit and there is an induced current. Alright, so how to determine the direction of induced current? Kita akan tengok sekejap lagi. Okay, so this is derivation of the equation of induced EMF in a straight conductor. Look at here, when this conductor is moving to the right here. Oh, tadi this one is moved to the left. Oh, sorry, this one is moved to the left, right? Okay, yang ni move to the right. Okay, so when the conductor here move to the right, okay, so here we have the change in area, okay, delta A, where the change of area here we have L, so here we have L times here we have dx, okay, L and this is dx, okay, dx tu adalah change of x lah, L dx, that's why we can write change of area is equal to L dx. So when we substitute in this equation, Okay, in Faraday's equation, okay, we can get this is the derivation of equation of induced EMF, which is finally we get BLV sin theta. Okay, saya tak tunjuklah derivation ni, saya rasa awak dah belajar kan? Okay, dalam kelas. Okay, so kita akan fokus kepada extra question. Okay, kita akan mula dengan example number 1. Okay, question number 1, we have the AC generator that consists of 8 turns of wire and the area is given 0.09 in meters squared. Okay, so area is 0.09 meters squared with the total resistance of the loop is 12 ohm. Okay, so the loop rotates in a magnetic field. So it rotates in a magnetic field of 0.5 Tesla and the frequency of the rotation is given as 60 Hertz. Okay, so as we know, when the loop or the coil is rotating in a magnetic field, so it will produce an induced EMF. Okay, and the equation, okay, the equation of the rotating coil when rotating in a magnetic field, so you can write that the induced EMF is equal to NBA, remember, NBA omega sine omega t. Okay, so remember we have discussed just now, okay, that when we have a coil that rotating, so it will produce an induced EMF. Okay, so this is the equation of induced EMF, okay, that related to the rotating coil. Okay, so omega is the angular speed. Alright, so we can calculate the maximum induced EMF. So question number 1, we want to calculate the maximum induced EMF. So the induced EMF will be maximum when the, so we want to find this one, when the sine omega t is equal to 1. Okay, so when sine omega t is equal to 1 means that the induced EMF is maximum. Therefore, induced EMF, the maximum induced EMF is equal to NBA omega. Alright, so from here, we can just substitute all the values that given from the question, but we don't have value of omega, right? Okay, but we know that omega is equal to 2 pi f. Okay, so from the frequency, we can find omega, where omega is equal to 2 pi f. F is 60 and omega is equal to, okay, awak boleh kira asing lah. Okay, so you can calculate separately or you can just substitute in this equation where omega is equal to, so the number of turns is given 8, B is 0.5, A is 0.09, and omega is 2 pi f. Alright, so I just substitute omega as 2 pi f in this equation. So saya tak kira asing. Okay, so therefore the answer is equal to 135.7 volt. Okay, so this is my answer. Okay, so second, what is the maximum induced current? Alright, so when there is induced EMF, when there is maximum induced EMF, so akan ada maximum induced current. Okay, so V is equal to IR, pernah jumpa, okay, based on the Ohm's law. Okay, so for here we also have the induced EMF, okay, is equal to induced current, maximum induced current times the total resistance in the wire. Okay, so the total resistance is given 12 ohm. Therefore, we can just substitute in order to calculate the maximum induced current, where I is equal to EMF is 135.7 over R is 12 ohm. Therefore, the answer is equal to 11.3 ampere. Okay. Kadang-kadang soalan dia tak tanya dulu, calculate the maximum induced EMF. Soalan terus dia tanya, calculate the maximum induced current. And then student blur. Macam mana nak cari induced current? Kan? Okay, so remember, before you calculate the induced current, you must calculate first what is the induced EMF. Okay, and you can relate. Okay, induced EMF, you need to relate the equation of induced EMF with the equation of rotating coil. Okay, yang kita dah belajar. Okay, next, determine the induced EMF. Okay, determine the induced EMF as a function of time. Means that we need an equation of the induced EMF in terms of time ataupun as a function of time. Okay, so the equation of induced EMF, okay, as we know, the general equation is NBA omega sine omega t. Remember? So this is the equation, right? Okay, but now, okay, we have all the values and B, A, omega. Okay, so we can just substitute. Okay, so let's calculate first. What is the value of omega? Since it's equal to 2 pi f and f is equal to 60 hertz, then I can substitute 2 pi times 60 and I would write as 120 pi radian per second. Okay, I just leave the answer for omega in terms of 120 pi. Okay, so the induced EMF, okay, is equal to, remember this value, okay, that we calculated just now, NBA omega is 135.7. Then we can just write here 135.7 sine omega is 120 pi and times t. Okay, so finally look at here. Okay, we have an equation of induced EMF which is in terms of t. Okay, let's say we want to calculate what is the induced EMF. Okay, at t is equal to 5 seconds. Okay, then we can substitute in this equation. Okay, so yeah, finish example number 1. Let's proceed to example number 2. Okay, example number 2, we have a figure here. Alright, and I try to transfer a figure from a question to a real diagram. Okay, for example, here I have a circular shape of a loop. Okay, let's say the pink color here is a loop of wire. Okay, and the question states that, okay, we have a uniform magnetic field of magnitude 0.29 Tesla, makes an angle of 13 degree with the plane. Okay, 13 degree with the plane of a circular loop of wire. So let this pink shape is the loop. Okay, so the loop has radius of 1.85 centimeter. Make sure you change to meter and determine the magnetic flux through the loop. So you want to determine the magnetic flux of the loop, where the equation is equal to BA cos theta. Okay, so from this equation, obviously we need to find what is the area of the loop and then what is the angle between. Okay, remember this is the angle. Okay, angle between, okay, between the vector A and the magnetic field B. Okay, so but the question states that the 13 degree angle, okay, is the angle between the plane of a circle loop of wire and the magnetic field. Jadi kalau kita baca betul-betul soalan tu, alright, so here we have B, alright, and the angle is here. This is the angle. Okay, so the angle is here, 13 degree. Okay, it's the angle between, because the question states that the uniform magnetic field B, okay, the uniform magnetic field B here makes an angle of 13 degree with the plane of a circular loop. So this is the plane, Okay, the pink color is the plane and this is B. And they are 13 degree. But when we look at this equation, okay, the magnetic flux equation, theta is the angle between the vector A and B. Vector A must be perpendicular to the plane. Okay, so let's draw vector A. So here we have the plane. Okay, so this is the plane. So you must draw that the vector A must be 90 degree to the plane. Okay, so this is 90 degree and this is also 90 degree. Therefore, the angle theta between A and B is not 13 degree, but it's 90 minus 13 and it's equal to 77 degree. Okay, so please read the question carefully. Okay, so now we can just substitute in this question, but before we do that, we need to calculate first what is the area of the loop, which is the equation is equal to pi r squared. Okay, where r is given as 1.85 cm. Okay, ini pun baca betul-betul soalan bagi radius ke bagi diameter. Okay, so just substitute here where the magnetic field is 0.29 and let's substitute the area pi r squared. Pi times r is 1.85 cm squared. Okay, and times cos 77 degree. Okay, so make sure your calculator is in degree mode, not in radian mode. Okay, so the answer is equal to 7.01 times 10 exponent negative 5. Okay, the unit is Weber. Okay, so the unit is Weber. Okay, so this is the answer. Okay, so finish question number 2. Easy, right? Okay, so let's proceed to question number 3. Okay, question number 3. So we have a magnetic flux passing through a single turn of coil. It's increased quickly but steadily at a rate of, okay, so baca betul-betul, at a rate of 5.0 exponent negative 2 Weber per second. So tengok pada unit dia pun kita tahu it's a rate change of magnetic flux d phi over dt. Okay, so it's equal to 5.0 exponent negative 2 Weber per second. Okay, d phi, the unit for magnetic flux is Weber. Okay, and over dt, the unit for time is second. Okay, this one second. Okay, so now we want to calculate if the coil have 500 turns and is given 500 turns. Okay, dia kecilkan sikit. Okay, calculate the magnitude of the induced EMF in the coil. So this is very simple since Faraday's law state that induced EMF is directly proportional with the change, okay, the rate change of the magnetic flux. Alright, so we can just substitute in this equation. Okay, so yeah, simply straightforward. Okay, and this is negative 500 and this is 5.0 exponent negative 2. Okay, so dalam soalan ni tengok saja pada unit Weber per second. Okay, okay, dia dah kata that the magnetic flux increase quickly, okay, at rate of, okay, rate of tu pada kadar berapa. Okay, so kalau student dia tak tahu, yang soalan bagi tu adalah d phi over dt, so dia boleh jadi blur lah, kan, ada blank, padahal soalan senang je kan. Okay, so the answer is negative 25 volt. Okay, where negative signs to indicate that it's a direction of the induced EMF which is opposed. Okay, oppose the changes in the coil. Okay, so this is the answer. Okay, so finish question number 3. Okay guys, example number 4. Alright, if you look at here, I have a diagram. Okay, where this diagram, okay, I tried to sketch this diagram by myself. Okay, kalau awak tengok gambar tangan ni, Gambar tangan ni sebenarnya gambar tangan saya sendiri, okay. Saya tangkap gambar tangan saya sendiri. Lepas tu saya letak dekat sini, okay. Lepas tu saya edit lah, okay. So, a circular coil, okay, tengok pada soalan A circular coil has N equal to 200 turns and the diameter is given 36 cm. Okay, so let's take out all the information. So, N is equal to 200 and the diameter is equal to 36 cm, where the radius is equal to, so let's change the radius to 2 meter lah. Okay, kita tukar terus 36 cm. Okay, let's change to meter and it's equal to 0.18 meter. Okay, and the resistance of the coil, okay, tengok pada bulatan ni. Okay, this circle, let's say this is a coil. Okay, I try my best to draw a 3D diagram. Okay, but I don't find any coil, 3D coil. So this is, so just assume this is a coil. Okay, okay, alright. So the magnetic field, okay, given that the resistance of the coil is 2.0 ohm and the uniform magnetic field is applied perpendicularly to the plane of the coil. So you can see here we have the red arrow here, where this arrow is the uniform magnetic field that applied perpendicularly to the plane of the coil. So this is the coil and we try to apply the magnetic field that is perpendicular to the plane of the coil. Okay, so let's write that the resistance of the coil is given 2.0 ohm and we have the magnetic field is 0.5 Tesla. This is initial magnetic field and the final magnetic field is 0 Tesla. Okay, and the change of time, and it's happened in 0.8 second. Okay, so let's take out all the informations given by the question, since that the question state that if the field changes uniformly from 0.5 Tesla to 0 Tesla in 0.8 second. Okay, you can see here, okay, we have the change in magnetic field. Okay, so there is a change in magnetic field. Okay, so saya tulis kat sini, there is a change in magnetic field. Okay, so we have dB over dt. So when there is a change in magnetic field, so there is a change in magnetic flux, okay, in a coil. So when there is a change in the magnetic flux, so there is an induced EMF produced. Okay, so let's write the equation, okay, of the induced EMF, as we know that induced EMF is equal to negative NA cos theta, and this question related to the change of the magnetic field dB over dt. Okay, so we want to find the induced EMF and current in the coil while the field is changed. Okay, and then we need to determine the direction of the current induced. Okay, so let's start question number, let's start question A. Okay, let's put here as question A. Okay. Okay, so now I want to just substitute all the values given. So N is 200, where A is pi r squared, pi where r is 0.18 squared, and cos, okay, cos theta. So look at here, okay, so theta is the angle between B and A. Okay, you can see here, okay, awak boleh tengok direction of B in this direction, okay, ke sana, okay, and A pun ke sana lah. Okay, A must be perpendicular to the plane, so angle dia kosong. Okay, macam ni lah, B ke sana, A dia pun ke sana juga, boleh. So angle dia kosong, so kita boleh tulis cos 0, so it's equal to 1 and dB dt B final minus B initial over time. The change of time is 0.8. Okay, therefore the answer is equal to, okay, so the answer is equal to, okay, 12.72 volt. Okay, so kita dah jawab. Find the induced EMF. So it's equal to 12.72 Okay, but now we want to calculate what is the induced current. So the induced EMF is equal to induced current times the total resistance in the circuit. Okay, so therefore the induced current is equal to 12.72 over R. The resistance is given 2.0 ohm. Okay, and the answer is 6.36 ampere. Okay, so we finish question A. So the current in the coil, okay, is 6.36 ampere. Okay, so for part B, we want to determine the direction of the induced current. So we need to apply the Lenzs law, okay, and the right hand grip rule that we have learned in class. Okay, so look at here. Okay, so based on the Lenzs law, okay, so what happened? Okay, so now what happened? Okay, the magnetic field change daripada mana ke mana? Okay, kita tengok balik. The magnetic field change from 0.5 Tesla to 0 Tesla. Means that the magnetic field is reduced. The magnetic field is reduced. Dia berkurang. Okay, so from here, okay, awak tengok dulu yang tulisan hijau ini. Okay, look at here, the green one. Okay, so let's say we have north and south. Okay, so we have north and south which is perpendicular. Okay, let's say kita ada direction of B ke dalam macam ni, north and south. Boleh? Okay, good. And then, okay, and then we want to determine what? Okay, and then we want to determine, okay, kenapa saya lukis macam ni? Oh, saya lupa nak beritahu awak kenapa saya lukis macam ni. Okay, sebab soalan dia bagi dalam bentuk ini. Okay, saya lukis kat awak ya. Okay, soalan bagi dalam bentuk ini. Okay, dia bagi into the page B. Dia bagi B into the page. Okay, so this is B, this is the coil. So B is into the page. Okay, into the page. So since B is into the page, that's why saya lukis 3D diagram saya is into the page. Alright, so if B is into the page, so here is, the green color here is north and here should be south. Alright, so since the question state that the magnetic field here is decreasing, okay, B is reduced, decrease kan, daripada 0.5 to 0. Okay, so based on the Lenzs law, B induced would produce in the opposite direction. Okay, so kalau sini north, sini south, so kawasan sini dia akan jadi, kat sini dia akan jadi apa? Sini dia akan jadi south. Betul? Okay, so sini dia akan jadi south supaya dia boleh attract more magnetic field. Okay, in order to maintain its initial condition. So sini akan jadi north. Okay, so since here is south and here is north, so when you use your right hand grip rule, okay, macam gambar ini yang saya lukis ni, saya letak tangan saya kat situ, and then you can look at the direction of the other fingers. Okay, the other fingers should be pointing in this direction, which is clockwise. Okay, so you can see here that the direction of the magnetic field is in this direction. Okay, dia sama, the same direction. Dia macam ni. Okay, yang hijau ini is the direction of B induced. Okay, remember, okay, at the beginning of this video, okay, I have explained that if the magnetic field is decreasing, sama macam soalan ni, okay, when the magnetic field is decreasing from 0.5 Tesla to 0, then the induced magnetic field will act in the direction which is same direction. Okay, same direction of the applied field. Okay, so this is the applied field yang color merah. So this is direction of the, yang color hijau is the direction of the induced magnetic field. Okay, and okay, kalau B decreasing, the direction of the induced magnetic field will act in the same direction. Okay, kalau B dia increase, the direction of the induced magnetic field will act in the opposite direction. Okay, boleh? Okay, so now in order to determine the direction of the induced current, okay, guna tangan kanan, right hand grip rule. Okay, let's point your thumb to the north direction, okay, ke atas. So your jari yang lain akan ke arah clockwise. Okay, so dia akan jadi macam ini. Okay, so the answer is clockwise direction. Boleh? Boleh tak? Okay, good. Okay, kat situ. Okay, so let's proceed to question number 5. Okay, question number 5. Okay, so look at here, we need to calculate the current through a resistor. So here we have the resistor R, where the resistor here is 37 ohm. Okay, so the resistor is connected to a single turn circular loop where the diameter is given 10 centimeter. Okay, so let's write all the information given. Okay, when D is 10 centimeter, then R is equal to 5 centimeter. Okay, which is 5 exponent negative 2 meter. So assuming that the magnetic field through the loop is increasing, okay, so dia dah sebut that B is increasing. Okay, so B is increasing. So there is a change in the magnetic field where the rate of change of the magnetic field is equal to, so dB over dt is given 0.05 Tesla. Okay, so why the magnetic field through the loop is increasing? So look at to the diagram. So this question is come with the diagram. So look at this bar magnet, where this bar magnet is come closer to this coil. Alright, so now look at this bar magnet, where this bar magnet will come closer to this coil. That's why there is a change of the magnetic field, where the magnetic field in the loop will increase at a rate of 0.05 Tesla per second. Okay, and second thing you must consider, okay, please focus on the north and south pole of the bar magnet. So here we have the south pole here, and this is the north pole. Okay, so the question asks us to calculate the induced current and state its direction. But before we calculate the induced current, we need to calculate first what is the induced EMF, right? Okay, so let's start to calculate the induced EMF. Okay, so I want to calculate the induced EMF, okay, where the equation is equal to, okay, remember, negative N A dB over dt, where cos theta is equal to cos 0 and cos 0 is equal to 1. Okay, so let's substitute all the values. Okay, sorry, I think I need to write here. Okay, where the induced EMF is equal to negative NA dB over dt, where N is 1 and A is pi r squared. Pi r is 5 exponent negative 2 squared. Okay, and times dB dt is given 0.05. Okay, and induced EMF, okay, make sure you check and calculate by yourself so that you familiar how to use your calculator. Okay, so jangan tengok saja, mesti salin dan kira. 3.93 exponent negative 4 volt. Okay, sorry, this is the induced EMF. The question asks you to find the induced current. Okay, so therefore the induced current is equal to EMF over R, where it's equal to 3.93 exponent negative 4, and R, the resistance is given, is it 37? Okay, so it's 37 ohm, and it's equal to, okay, the current is, okay, let's put I induced, and 1.06 exponent negative 5 ampere. Okay, so this is the answer. Okay, but how about the direction? How about the direction of the induced current? Okay, so now let's refer to the question. Okay, so since the magnetic field is increasing, okay, look at here, the bar magnet will move closer to this coil, okay, or this loop. Okay, what happened? Okay, B will increase. Okay, and the induced magnetic field in the loop will try to oppose the change of the magnetic flux. Okay, so this side will be south and this side will be north. Okay, so you can see here, when the magnetic field is increasing, the direction of the induced magnetic field here is in opposite direction. Okay, so remember, okay, magnetic field here, so here is the direction of the, and this is the direction of magnetic field from the bar magnet. Okay, and the direction B is in this direction, okay, upward, and this is downward. Okay, you boleh nampak direction dia opposite kan? Ni B dia ke atas, okay, and ini B dia ke bawah. Okay, so okay, remember, so when B is increasing here, when B is increasing, so focus on the south pole here. Okay, so since this is the south pole, so the coil will try to oppose the change in the magnetic field and also the magnetic flux in the coil. So this side should equal to south pole. Okay, dia akan sama lah south supaya dia boleh repel. Okay, and this would become north pole. Okay, and then take your right hand grip rule. Okay, so saya padam ni dulu. Okay, ni supaya awak nampak. Okay, and then use your right hand grip rule. Okay, let's point your thumb to the north. Alright, and then look at your other fingers. Okay, dia akan curl ke arah, okay, ke arah anti-clockwise ke sini. Okay, in this direction. Okay, so dia akan gerak sini lah. Boleh. Okay, so soalan tanya, what is the direction? Calculate the induced current and state its direction. So the direction is anti-clockwise direction. Okay, anti-clockwise. Boleh? Okay, so kita boleh tengoklah dekat situ. Alright, so finish question number 5. Okay, so here we have question number 6. Okay, so consider the arrangement shown below. So here we have the arrangement, and assume the resistance, okay, of the conductor is 6 ohm. Alright, so R is given 6 ohm. Okay, and the uniform magnetic field is 2.5 Tesla. So B is 2.5 Tesla, is directed into the page. Alright, so A, we want to calculate at what speed should the bar be moved to produce a current of 0.5 ampere in the resistor. Alright, so if you look at here, alright, so this bar from A to B, so the resistance here R is 6 ohm. Alright, and the bar will move to the right. Okay, and here we have the magnetic field which is into the page. So when the conductor is moved to the right, so what happened? There is an induced current that flow in the resistor, and the amount of current that flow in the resistor is given as I is equal to 0.5 ampere. Okay, so you want to calculate what is the speed. Okay, so what is the speed, and B, what is the direction of the induced current. Okay, so before that, let's write the equation of the induced EMF for the moving conductor. Okay, when the conductor is moving through the magnetic field, so it will produce an induced EMF where it's equal to BLV sine theta. Okay, so where theta is the angle between, it's angle between V and B. Okay, you can see here, okay, V is to the right. Okay, you can see here V is to the right. Okay, and B is into the page. B is into the page. Okay, V is to the right. Okay, and B is into the page. Awak tengok 3D lah. Okay, B masuk ke dalam screen. Kalau awak tengok handphone awak sekarang ni, B is into the page, V is to the right. So the angle between them is 90 degree. So here is sin 90 is equal to 1. Okay, if you look at to this question, we cannot use this equation since we don't have the velocity V, okay, and we don't have what is the induced EMF. Okay, we want to find V and we don't have what is the induced EMF. Okay, but we are given the amount of the induced current and what is the value of resistance. Then we can write that induced EMF is equal to induced current times R. Okay, therefore from here we can find first what is the value for induced EMF, or we can straightly substitute. Okay, EMF is equal to IR in this equation. Therefore I induced R is equal to BLV. Okay, therefore V is equal to I induced R over BL. Okay, so from this equation we can straightly substitute. I induced is given 0.5 times the resistance is 6 ohm and the magnetic field is 2.5 and the length of the bar is given 1.2. Okay, therefore V, okay, we want to calculate what speed should the bar be moved to produce a current of 0.5 ampere in the resistor, and the answer is 1 meter per second. Okay, alright, so this is the answer. Okay, but for B, what is the direction of the induced current? Okay, in order to determine the direction of the induced current, so you need to use the Fleming's right hand rule. Okay, so maybe some of you will use the palm rule, but I'm going to show you how to use the Fleming right hand rule. Okay, so mana-mana you guna, pastikan you ingat dengan betul lah cara menggunakannya. Okay, jangan ingat dua-dua, nanti you terkeliru. Okay, so take out your right hand. Okay, so your thumb here, let's say we have, this is your thumb and it's your motion, which is V. Okay, and here is the magnetic field. Your index finger is your magnetic field and the middle finger is your current I. Okay, so we have VBI. Okay, so now V is to the right. Okay, you need to put your V is to the right and B is into the page. Okay, V is to the right and B is into the page. Okay, you can look at to the video here. Okay, I show you. Okay, V is to the right, B is into the page. So see here, so we have I is upward. So you can see I is upward. Okay, so I is upward. Okay, so saya akan lukis kat sini lah. Okay, let's take another color. Okay, so I is upward in this direction, I. Okay, the induced current in this direction. Okay, so in order to answer B, so I will write the direction of the induced current is, okay, anti-clockwise. Anti-clockwise. Okay, or what is the direction of the induced current? Anti-clockwise. Okay, ataupun kita boleh cakap it's upward. Okay, upward means that it's refer to the direction of the current, okay, in the conductor bar. Okay, boleh. Okay, so we finish question number 6. Let's proceed to question number 7. Okay, look at question 7. So the figure shows a rectangular loop of wire 0.5 meter wide and the long is 1.5 meter. Okay, and it's moving out of a uniform magnetic field. So the direction of V is given in this direction. Okay, and the magnetic field B is given B is 2 Tesla at a constant speed where speed is 2 meter per second. Okay, so the left side of the loop stays, so the left side of the loop stays inside the field when the right side is out. Okay, so the left side is stay in the field when the right side is out. So this is the left side, the yellow color is the left side, and this one, okay, the turquoise color is the right side. Okay, and given that the resistance of the loop is 0.5 ohm. Okay, so 1. What is the direction of the induced current in the loop? Okay, all right, so look at here. Okay, this is my hand. Okay, okay, this is my hand. Okay, I try to snap the picture. Okay, I try to give you in order to enhance your understanding. Okay, okay, so look at here, the direction of the magnetic field is out of the page. Okay, so please use your right hand. Okay, VBI. So make sure the position of your finger, your thumb, your index finger and your middle finger is 90 degrees to each other. Okay, please refer to the video. All right, so now we have VBI here, where you get here 6. So look at here, since the loop is moving to the right, so my thumb is pointing to the right, and look at here, my index finger is pointing out of the page. So dia keluar daripada screen awak. Okay, and what is the direction of the current? Okay, and the current is downward. So I put the video of my hand, how I'm doing it. So the induced current is downward, therefore, okay, we can put the direction. Okay, so the direction is downward. Okay, so the direction is downward, so in this direction. Okay, so kita consider yang inilah. Okay, kenapa saya kata saya consider yang ini downward? Sebab siapa yang ada dekat dalam magnetic field? Okay, this one. Okay, yang ini dia soalan kata tadi, okay, the right side is out, the left side of the loop stays inside the field when the right side is out. Okay, so we consider, okay, we put our hand, okay, VBI at this point, therefore the induced current is downward. Okay, so in this direction. Okay, so the answer for number 1 is anti-clockwise. Alright, okay, so second, okay, calculate the induced EMF in the loop. So this is related to the conductor that moving, okay, that moving to the right, okay, that moving in the magnetic field, BLV sine 90 degree. Okay, so B, so L, what is the value of L? Okay, so look at here, so we consider this side, okay, this side 0.5 meter length, okay, as our conductor. All right, so since we consider this point, okay, so B is equal to 2 and the length is 0.5, where V is given 2, therefore the induced EMF is 2 volt. Okay, and next, calculate the induced current. I think this is very easy for you to solve. Induced EMF is equal to IR, so I for the induced current is equal to EMF over R, and EMF is equal to, so just now we have calculated that EMF is, the induced EMF is equal to 2 volt, and R is given 0.5, therefore the induced current is equal to 4 ampere. Don't forget to put the correct unit for your answer. Okay, alright, so finish question 7. Alright, so now we reach to the last example. Okay, we have a rectangular coil of 45 turns. So let's take out the information given. So we have n is equal to 45 and it's rotating. So we have a rotating coil here at a constant speed where the and it's rotating with a constant speed and it's rotating in a uniform magnetic field where the magnetic field strength is given 0.3 exponent negative 2 Tesla. Okay, and the width and the breadth of the coil are 10 centimeter and 8 centimeter respectively. Okay, and let's try to sketch. So 8 centimeter, okay, and the breadth is 10 centimeter, right? Okay, so calculate the frequency of the rotation if the maximum value of the induced EMF is given. Alright, this is very easy. We just apply all the equations, right? So when we have a coil that rotating in a uniform magnetic field, so the maximum induced EMF is equal to NBA omega sine omega t. So this is a general equation. Since it's a maximum induced EMF is given 15 exponent negative 2, so this is equal to 1. Therefore, we can just substitute all the values. Okay, where 45, B 0.3 exponent negative 2, and the area you can calculate 8 exponent negative 2 times 10 exponent negative 2, okay, and omega. So we want to find the frequency, right? So you must know that omega is equal to 2 pi f, okay? So you can straightly substitute here where omega is equal to 2 pi f, okay? So here we can solve for f, the frequency. So the answer for frequency is equal to 22.1 hertz. Okay, so this is the answer. So means that the coil is rotating with the frequency of the rotation, okay, is equal to 22.1 hertz. Okay, so now we have finished example number 8. So means that we have finished discuss all the questions in this video. Okay, so yeah, thank you for your support and see you in part 2 for chapter 5. Okay, so don't forget to share and like and yeah, subscribe. Okay, see you. Assalamualaikum and selamat sejahtera.